Professor of Number Theory at the University of Cambridge. He's going to talk to us about what is, of course, one of the key ingredients in the proof of Fermat, namely modularity. And the title of this talk is Modularity, Old and New.
Well, thank you very much for the introduction. So what I really want to do today is just try and give a sense of the impact that Andrew Wiles's proof of Maslow's theorem has had on this particular part of number theory in the years since it was first published. The first thing I want to do is suggest a reference, which is the March 2017 issue of the Notices of the AMS. There are some nice articles in here which were commissioned, I guess, to celebrate Andrew being awarded the Arbel Prize in 2016. And I can see that there are some experts in the room and also some non-experts, and this is nice because I think there's something in here for everyone. I just want to begin by reading a paragraph from Chris Skinner's article in this edition of the magazine, because I think it really it summarizes what I want to say very nicely. So he says, what distinguishes a great mathematical proof? There is, of course, no definitive answer to this question. Certainly proofs of famous or important open conjectures can lay claim to being great. By this measure, Andrew Wiles's proof for Maslow's theorem is a truly great proof. But proofs that introduce new ideas or open doors to progress on problems that were previously viewed as out of reach also have their claims to greatness. As noted in the Arbel Prize citation, Andrew Wiles's proofs also achieve greatness by this second measure. So I think that there's a huge amount that's happened in number theory in the last 25 years that's really directly related to what Andrew did. I just want to give you some hints today as to what that is. So the title of my lecture is Modularity, Old and New. So the first thing I need to do is tell you what modularity is, and we've just seen and had it quickly removed an allusion to what that can mean, and we've also heard that there can be different formulations of the same concept, so I'm going to show you an analytic one. Okay, so this is what is modularity. And we're going to start at quite a basic level, thinking of this as a property that any Diophantine equation can have. So we'll start off with, let's say, a polynomial in some number of variables with integer coefficients. And we'll associate to a polynomial x or xf. So this is the algebraic variety that it cuts out. So this would be the set of points on which the polynomial vanishes. So if you know algebraic geometry, you'll know that this is really the definition of a scheme. And if you don't know algebraic geometry, you'll probably be scared of that word. But that's okay, because all you really need to be able to do is know that if R is any ring, you can take what we like to call the R points, which is just the set of n-tupled of elements of R on which this polynomial is 0. And you might like to take R to be the integers, in which case you really are looking at solving a Diophantine equation when you try to enumerate the elements of this set. But you also might consider other rings, like the fields of real or complex numbers, or maybe, let's say, a finite field, perhaps with p to the n elements. Of course, the example that first springs to mind, given that we are where we are, is something like this: x to the p plus y to the p plus z to the p. And then if you're trying to figure out what's in the set xs of z, then you're trying to prove Fermat's theorem. Okay, so what do we want to do with such a thing? Well, I want to say what it means for a Diophantine equation to be modular, and that means, for me, defining its zeta function. This is defined by a nice formula, so we'll write it down. So it's going to be a function of complex variable s. It's going to be a product of factors which are indexed by primes p. And what is the factor at the prime p? Well, it's a kind of generating function that describes the number of solutions, so the size of these various sets, in all possible finite fields. And if you're looking at the p factor, you're looking at finite fields of characteristic p. So here we should put the exponential of the sum of the size of x of fp to the m times p to the minus ms over m. Okay, so it's a function, and there's a simple example that you probably have seen before, if you're interested in number theory at all, which is the simplest possible choice of polynomial, namely f of x equals x. And in this case, well, in any ring R, there's a unique solution to x equals 0, which is just 0. So this set always has exactly one element, and zeta p x comma s is x of, well, if you just take 1 here, you get minus log of 1 minus p to the minus s, which is just 1 over 1 to the p minus s. So zeta of x of s is just the usual Riemann zeta function. And that's basically why we choose this definition of the generating function. So that this is meant to be a generalization of the notion of zeta function to any Diophantine equation. And now we can say roughly what it means for such a thing to be modular. We say x or xf is modular if the associated zeta function can be expressed in terms of modular forms, or rather can be expressed in terms of the zeta functions of modular forms. So let me just give you a simple example before we jump into the deep end with elliptic curves. This is quite a famous one. This is what happens when you take f of x to be polynomial in one variable, x cubed minus x minus 1. That's a polynomial discriminant minus 23, I think. And, well, the number of solutions, as long as you're looking at a ring in which p is non-zero, is going to be either 0, 1, or 23. And actually, you can prove, if you know a bit of the theory of modular forms, quite a bit, that the zeta function has an expression as zeta of s times, let's say, zeta of g comma s, where g is the modular form given by a Q series and here Q is e to the 2 pi I tau. Tau is an element of the complex upper half plane. Okay, so what is a modular form? What is its zeta function? Well, I need to tell you that in order for you to be able to interpret this. So a classical modular form is, well, people normally like to say it this way. It's a holomorphic function. Let's say g from the upper half plane to the complex numbers, which satisfies the transformation law. Let's say g of a tau plus b over c tau plus d equals c tau plus d to the k times g of tau. This is for all tau in the complex upper half plane, k being some fixed integer. And for all elements a, b, c, d in some finite index subgroup of the modular group. SL2Z. Okay, so that's the definition that people normally give, but probably it's better to think of these things as being just holomorphic sections of line bundles on modular curves. And that's the definition that you use to connect it with the definition of modularity that was previously on this blackboard. And how do you get a zeta function out of such a thing? Well, there's a nice subgroup of SL2Z, namely the matrices which are upper triangular with ones on the diagonal, and their action on the upper half plane is just by translation. So this subgroup of transformations is generated by tau goes to tau plus 1, and that means that any modular form will be more or less invariant under this group, or a finite index subgroup of it. And that means it has to have a Fourier expansion, and okay, that Fourier expansion will look something like this. And then the associated zeta function is what you get when you cross out q to the n and put n to the minus s to get a Dirichlet series. Okay, so of course one has to be a bit more careful than this, but this is just meant to be something to give you the idea. So there's a way to bridge this algebraic world of Diophantine equations and this analytic world of modular forms, and if you can find a bridge, then you can match up the zeta functions and, for example, prove that the zeta function of an elliptic curve has an analytic continuation. That's one reason why you might be interested in something like this. Okay, so let's talk about elliptic curves now. We've already seen these, but if we say our f is of this form, then the algebraic variety x that we're writing down is an open subset of a so-called elliptic curve. In fact, it's the complement of one point. And I'll call that E. And then the modularity theorem that, thanks to the work of Ribbit, applied Fermat's last theorem. So this is proved by Andrew, and then there's the companion paper by Tenner and Wiles that appeared together in the Annals, proves that any semi-stable elliptic curve E, which by definition means that it has only good or multiplicative reduction, so that's a kind of tameness condition, is modular in the sense defined above. That's modularity. Now, to actually say anything about it, or for mathematicians to actually be able to say anything about it, we have to look at modularity through a different lens, which is the lens of Galois representations. So that's what we need to discuss next. So as we've already said, if E is an elliptic curve over the rational numbers, we can associate to it a whole compatible family of Galois representations. So these will be, I'll write down the notation. Okay, so here Q bar over Q is an algebraic closure. And GQ is the so-called absolute Galois group. And L is any prime that you like. Where do these come from? Well, the key thing about elliptic curves that makes them so special is the fact that they are endowed with group structures. So you might say it's a commutative algebraic group. And that means in particular that if you look at the set of solutions, or set of points on the curve with coefficients in Q bar, this is an abelian group which receives an action of the Galois group. GQ. And, well, the whole group is probably a little bit difficult to think about. But if you think about just the L infinity torsion part, so that's the set of points which are killed by some power of the prime L when you multiply. Well, this is a group that you can actually understand. And Andrew already said before that if you take the 3 torsion, you get something which is Z mod 3 cross Z mod 3. In general, this you can think of as being, well, complex analytically, an elliptic curve is a product of 2 circles. So you get the L infinity torsion in the product of 2 circles, and this you can identify with QL mod ZL squared. That's a convenient way to think about it. So where does the Galois representation come from? Well, in one sense you've already got it, because you have a big Galois module which has a simple structure when you just think of it in terms of an abelian group. But just to nail it down completely, what you can do is form, let's say, the set of homomorphisms from QL mod ZL into the L infinity torsion. And then this will be isomorphic as an abelian group to ZL squared. So once you make this choice of basis and you look at the action of the Galois group, you get a representation like this. The key reason why Galois representations are relevant for modularity is that they all know, even any single one, the zeta function of the corresponding elliptic curve. And this is something that's true not just for elliptic curves, but it works for any class of Diophantine equations. And the reason is, well, it's the existence of Frobenius elements. So for any prime p, there is a special element in the Galois group called a Frobenius element. Okay. And in fact, it's defined only up to some ambiguity, but that's not relevant for us. And it's a fact that for all but finitely many primes p, so in particular you want to avoid the primes where your curve has bad reduction, but once you do that, you have an equality trace of your Galois representation evaluated on the Frobenius element. This is equal to p minus the number of points in the affine part modulo p. Yeah. And this is true for powers as well. So if I take phi p to the n and put p to the n everywhere, I get a similar equality. And of course, we know that the zeta function is defined using these pieces of data, so this means the Galois representation on its own is enough to be able to study the zeta function, and therefore it's reasonable to think that it's enough to study the modularity property as well. And this, by the way, you can think of, if you like, as being a special case of the Grothendieck-Lefschetz trace formula in Italca homology. So that's the formalism that you'd have to apply if you wanted to think about a similar kind of result for the zeta function of a general Diophantine equation. In the context of elliptic curves, you can do things in a much more down-to-earth way. Okay. Right, so what's the consequence? Well, the consequence is that you can reformulate what it means for an elliptic curve to be modular solely in terms of its Galois representation. Or any one of its associated Galois representations. So E is modular exactly when there exists a modular form G let's say a n q to the n, such that if we call this number ap of e, that's the traditional notation, maybe I should call this bn to avoid being confused, such that ap of e is equal to bp for all but finitely many primes p. Okay, so that's a slight change in point of view. Instead of looking at the zeta function, you're looking at this more linear algebraic object, the Galois representation. But this point of view is what lets you prove the following theorem, which is also in those two papers. And this is the first example of what's called a modularity lifting theorem. And it's really decisive. So what does it say? Well, I'll just state a special case. So let's take E to be an elliptic curve. And let's take L to be a prime. And let's suppose that there exists a modular form let's say g of tau, such that, and you have to read this carefully to make sure you understand, such that for all but finitely many primes p, AP of E is not equal, but is congruent to B sub P modulo L. Then, if some additional technical conditions hold, E is modular. Okay, so let's look at this again. So in our reformulated definition, an elliptic curve E is modular if you can find a modular form whose Fourier coefficients are matched up with these numbers. I guess this would be the number of points on the elliptic curve modulo P, slightly massaged. Now what we're saying here is, if you want to get modularity, it's enough to check that there's a modular form that has that property modulo L. So that's something much, much weaker, because if you're thinking of these in terms of mod L Galois representations that we'll look at in a moment, this is a finite amount of data that you have to check. Whereas this looks like something where you're imposing infinitely many conditions at the same time. Yeah, so this is really much, much easier to check in practice than exhibiting something like this from scratch. And indeed, once this theorem is proved, sorry? So you fix the curve and the prime, then you have to check this condition. Yeah. So one thing to emphasize is that I've said there are technical conditions, but I haven't said what they are. So probably one condition you need is that L is not 2. But certainly you only need to check it for one prime L. You don't need to check it modulo infinitely many primes. Okay, so having proved this, Andrew is able to proceed directly to the modularity of semi-stable elliptic curves over Q. And this is a really beautiful argument which you mentioned already, but I want to talk about it again because it's so nice. Just check where I am. Yeah. So this is the idea that we saw. The idea is to take L equals 3, so to look at one particular Galois representation associated to your elliptic curve. So let me write this slightly differently by decorating this arrow. And then to think about how you might verify the residual modularity condition. So if you're only interested in integers modulo 3, then the natural thing to do is to first project down from GL2 of Z3 to GL2 of F3. So here you're just saying, well, there's a surjective ring map like this, so that gives me a map on GL2 as well. And then this gives you what's called the residual representation. So instead of looking at the action of the Galois group on the 3 infinity torsion, you're just looking at the action on the 3 torsion points of the elliptic curve. And the remarkable coincidence is the fact that this group homomorphism has a splitting. So if we let's see, rho bar tilde be discomposed the splitting, well, note that this representation, even though it goes from the Galois group to GL2 of Z3, it's very different to the one you started off with, because this is going to have infinite image. Indeed, it'll often have open image in GL2 of Z3. Whereas this homomorphism has finite image, because you're mapping down to a finite group and then applying an injective group homomorphism. So this one, rho bar twiddles, and this one, the original rho, are very different, but they have the key property that, well, they're equal modulo 3, or another way of saying that is, for all but finite many primes p, the trace of rho of the Frobenius element, which is what is meant to be AP of E, this is congruent modulo 3 to trace rho bar twiddles of Frobenius element. So that means if you can show that this Galois representation is modular, then you can get the modularity of this one modulo 3, and then this theorem goes to the full modularity of the elliptic curve. And you can prove modularity of this representation essentially by, well, the result is the Langlands tunnel theorem, but the reason that they're able to do that is because the group GL2 of F3 is a solvable group. Something which is, of course, not true for any GL2 of Fp for p being 5 or greater. PSL2 of F5 is A5, and PSL2 of Fp for larger values of p, well, those are just their own simple groups. So this is something that really only works for the prime p equals 3, and it's an amazing coincidence that the whole thing hangs together in the way that it does. Now that works if certain technical conditions modulo the prime 3 for your particular elliptic curve of interest are satisfied, but they're not always satisfied. And then there's another beautiful argument which I don't want to go into, which people call the 3-5 switch. Which allows you to try and do the same argument, but with a different representation, namely the mod 5 representation instead. So I think there's a certain amount of help from the law of small numbers here. Okay, so that was just a very quick sketch of some aspects of the proof of this theorem and its application to the modularity of elliptic curves. But what I now want to do is talk about some things that have happened since the proof, which build on what was done by Andrew Wiles in different ways. So this, I guess, will be a new section called Generalizations. And I've got a few different things to go through, and if you've got time, then hopefully we'll get to the work of both Fields medalists in number theory this year. But the first one I want to talk about is extensions of the so-called Taylor-Wiles method. Okay, so to understand what I'm talking about here, I need to tell you a bit more about the structure of the proof of this key modularity lifting theorem. And well, the main idea is to reformulate it slightly by writing down a diagram which is very evocative for number theorists of a certain stripe. That's to consider a diagram from one ring called RS to another called TS. Okay, so S here is meant to be some finite set of primes. And what are these objects? Well, they're rings. This is a ring homomorphism. And we're supposed to be able to think of them as moduli spaces for certain kinds of objects. So the first one, R, well, I'll just write down what its homomorphisms are to ZL. So this is supposed to be more or less a set of Galois representations to GL2 of ZL, such that rho is, on the one hand, unramified outside S, and on the other hand, satisfies the condition that the mod L representation associated to rho, so that would be to GL2 of FL, this is equal to the residual representation that you're interested in. And then what's TS? Well, it'll be characterized by the fact that its homomorphisms to ZL correspond to those Galois representations which come from modular forms. Let's just say rho is modular. Okay, so this is the diagram, and what you ultimately want to show is that this map is an isomorphism, which of course implies that this inclusion from modular Galois representations to all Galois representations has to be an equality. And then you apply this with S taken to be a set of primes where your elliptic curve E has bad reduction together with a prime L, and then your Galois representation corresponding to your elliptic curve will be a homomorphism from RS to ZL. And then you apply this equality to deduce that it comes from a modular form. So that's the structure of the proof. Why is that useful? Well, it gives you the freedom to vary S. And any time you are doing this kind of number theory and you can vary the set of primes where ramification is allowed, you're happy, because that gives you an enormously powerful tool. So the proof then proceeds in two steps. The first one is to show this is an isomorphism in the case where S is as small as possible. And then the second step is to proceed from this to the general case by comparing with the first case using so-called numerical criterion, which was a beautiful piece of commutative algebra that was invented by Wiles for this purpose. Okay, so I'll come back to a discussion of the numerical criterion later. But here I want to concentrate on the first step, and this is what is carried out using what we call the Taylor-Wiles method. And I don't want to go into any real detail of what this actually is, except to say that this really relies very heavily on the possibility of being able to vary the set of primes where ramification is allowed, and then seeing what happens when you allow more and more ramification. And I think there's a lot of discussion of this in the famous Horizon documentary, so you can go there for more information if you want to. What I do want to say is how this has been generalized. And there are just a few key developments that I want to refer to. The first one is a work by Fred Diamond that came out pretty soon after Fermat was proved. And this is a change in point of view that allows you to apply the method to much more general classes of modular forms than you might initially think. And another work that's very important is by Kizin, and he introduces a new technique which allows you to consider much more complicated kinds of local ramification than had previously been allowed. And there's another useful input, which is a paper by Chris Skinner and Andrew Wiles, which is very useful for removing ramification. And taken all together, this body of ideas means that if you're interested in things like modularity of elliptic curves, you can very often get very far without having to proceed to the second step in the proof. And just to give you one standout result that's been proved using this circle of ideas and also some hard Diophantine geometry in recent years. I want to state a theorem by Nuno Freitas, Baolei Hung, and Samir Sigsek. And what they proved is that any elliptic curve over any real quadratic field is modular. So this may be actually the first time that anybody proved the modularity of elliptic curves over infinitely many number fields. I think Samir is here, so he'll correct me if that's wrong. He's not correcting me, so I must be right. Okay, so that's one direction that people have carried on moving in. Another one is the creation of the notion of potential modularity. So this notion is, I think, due to Taylor, and it's a response to the question, what happens when you can't do the 3-5 switch? So one of the things that allows you to use the 3-5 switch to prove modularity of semi-stable elliptic curves over Q is another coincidence, namely that x naught of 15, so this is the modular curve which parameterizes elliptic curves which have mod 3 and mod 5 Galois representations being reducible. And it has genus 1, so a priori it might have infinitely many rational points, but it turns out to be the case that this is finite. And also, none of its rational points correspond to semi-stable elliptic curves. Okay, so the converse of that is, if you have a semi-stable elliptic curve over Q, then always at least one of the mod 3 and the mod 5 representations is irreducible. And that's essential to be able to apply a modularity lifting theorem. But of course, I mean, in another world, this genus 1 curve might have had infinitely many rational points, and then you could have been stuck at this point. Well, It depends whether you think mathematics is the same or different in other universes. But in this one, we're lucky, so we have a finite number and everything is okay. But of course, if you go to other number fields, for example, if you go to real quadratic fields, you will find number fields for which this genus 1 curve does have infinitely many rational points. And then it seems like you're stuck if you just want to do a straightforward generalization of the proof. So Taylor introduced, I think, this technique that allows you to get around this, but only if you're willing to not quite get modularity, but only to get something called potential modularity instead. But this is still good enough if you're interested in, for example, proving that the zeta function of elliptic curve has a meromorphic as opposed to an analytic continuation. And let me just state one theorem due to Taylor. And this says any elliptic curve over any totally real field is modular. Sorry, potentially modular. And potential modularity, I should say, is not just something that we know how to apply to elliptic curves. We know how to apply it to much more general classes of Galois representations as well. It's something that plays an essential role in the proof of the Sartre-Tate conjecture for elliptic curves. And it also is something that you can feed back into the theory to get information about, for example, Galois deformation rings. So it's a really flexible and useful notion. Okay, so I think just a couple more things that I want to mention. The third one is still more recent than the first two, and this is generalization by Caligari and Garrity of the same Taylor-Wiles method to what they call the positive defect situation. So I don't have time to get into the precise definition of the positive defect situation, but let me just say that this includes, for example, the situation where you want to prove something like modularity of elliptic curves over imaginary quadratic fields. And the reason why this situation is intrinsically more difficult is the several equivalent reformulations of the notion of modularity that we have access to over Q no longer apply in this situation. So you have a much more limited set of tools that you can work with. And here we have recent work of Scholzer, and he allows us to understand the Galois representations attached to torsion classes in this setting. To prove unconditional results using the Caligari-Garrity circle of ideas. And there are two papers that I know of that are currently in the works that aim to do something like this. One of them has just been made publicly available. So the first one is a 10-author collaboration which will prove potential modularity of elliptic curves over imaginary quadratic fields, and also the Sartre-Tate conjecture for such elliptic curves. And the second is a paper by Caligari, Boxer, Caligari, G, and Poloni, and they prove the potential modularity of abelian surfaces over Q. So those are two very exciting theorems, I think. The final thing I want to mention, so this is where our second Fields medalist comes in, and this is more of a question than something that's been done already. But this is the question of reintroducing the numerical criterion, which is one of the most beautiful parts of the original paper by Andrew, into the mix. And the problem is that it fails to hold in the positive defect setting. For example, in the setting of modularity of elliptic curves over imaginary quadratic fields. And the reason is that the Galois deformation ring doesn't grow as much as you expect when you allow more ramification. So passing from S to a larger set, S prime containing S. So in the defect zero situation, there's a precise measure of how much this ring grows in size, and that measure will be equal to basically the p-adic valuation of a special value of an L function. In general, for example, in this imaginary quadratic setting, you'll only get an upper bound. You won't expect to have an equality in general. And there's the question of whether you can rescue this. And it's made feasible because Venkatesh has defined, let me say, derived or homotopy theoretic versions of the Galois deformation ring and also of the Hecker algebra. So if you take homotopy groups, then instead of just having a ring, you have a graded ring which has the classical object as its zeroth graded piece. And the question is, can we recover the numerical criterion if we use these objects? Okay, so this is of course a question aimed really at experts, but I wanted to have something to keep them interested to the end. And I'll stop there. Thank you.
Questions?
So these are torsion classes of what exactly? You mean here in the cohomology?
So here I mean if I take GL2 over CM field and I take the group cohomology of the arithmetic groups, I want to A, know that the Galois representations associated with those torsion classes exist, and B, know that they satisfy the expected conditions coming from p-adic Hodge theory. So Scholze, of course, constructed the Galois representations, and then one of the things that's going to happen in this 10-author project is to use the vanishing results for Schmall varieties, which are proved by Cariani and Scholze, to prove that kind of local global compatibility at P for the torsion classes using a reduction from GL2 to U22, basically.
If there was an elliptic curve which was potentially modular but not modular, then how could you tell? How would you notice? What would it look like? Is this something you could investigate experimentally?
That's a very good question. And of course, and I'm sure many of the people in private have tried to prove that a potentially modular elliptic curve is modular, but not knowing that much about zeta functions really, I couldn't do anything, and no one else has ever shared the results of their private investigations with me. So I'd love to know the answer to that question, but I'm afraid I don't have an answer myself.
There's an obvious question: what varieties are modular? Is it plausible that all semi-stable abelian varieties over Q are modular?
I certainly would believe that conjecture, yes. And in fact, if you want to give a really precise conjecture, so for elliptic curves, I mean, now we know the theorem, but even before the theorem is proved, one could say, well, if I have an elliptic curve, I have its conductor, and I expect to be able to find a modular form of that conductor. Now, if you want to be able to formulate an analogous conjecture for abelian varieties of high dimension, you need to know a little bit about the representation theory of the group on the automorphic side, which would be GSP 2n of QP. But I think people have now kind of generalized the theory of new forms to the extent that there is a conjecture for abelian varieties which is as precise as the original conjecture for elliptic curves. And there's a recent preprint by Benedict Gross, which is on his homepage. I don't know if it's been published or not, where he lays that out in a very clear way. Yeah, but certainly the conjecture includes a statement that any semi-stable, or indeed any abelian variety over Q, is modular, being associated to an automorphic representation of, I guess, GSP2G of the Adels.
So this workup shows you on the torsion. Does that use Piaget-Hodge theory or integral Piaget-Hodge?
So his construction of the Galois representations. I mean, and it really uses the theory of perfectoid spaces, and I'm not sure I know how to separate that from Piaget-Hodge theory, but I don't believe that it uses any Piaget-Hodge theory in the classical sense. Like, I don't think any of Fontaine's period rings make a direct appearance. But he does use, for example, the results appearing in his Piaget-Hodge theory paper, where he shows how to calculate the cohomology of a rigid space with FP coefficients in terms of kind of Piaget analytic or perfectoid data. So what we might call classical Piaget-Hodge theory doesn't make a direct appearance, but certainly it's kind of living and breathing inside all of his arguments.
Okay, well, if there are no further questions, let's thank Jack for a very beautiful talk.